Can we continue? Do you hear me?
Yes.
Okay, so let's just try to explain. So your question was, is it always an optimal solution when you do observational method?
Yes. The case B, for example.
Here, yes, yes. So this is in case B. This is traditional design. You start with the lower bound parameters. So if you start with the lower bound, the lower value of possible parameters, then yes. But if you use this in the traditional design, then you will have this line here. But the real condition will be here. That means you will have the failure of the construction if you decide for the you will have the reduction of the parameters in comparison to this. But if you start with the lowest value of parameters, then the true parameters are actually better, and you have some cost reduction. So you have the cost reduction here. Here you have the increment of the cost, but you're saving the structure from failure. So whenever it's possible to apply the observation method, it can bring some cost reduction. If it doesn't bring the cost reduction, that means you save the construction from the failure. See, the real parameters are this, and you adapted this parameter better than this. Due to that, you have failure. Even here, you have increment. You are updating parameters that are better than you suggest. Of course, they are worse than some average values, most probable values, but still it's better than this one if you use in traditional design as the lower value of the parameters. But since it's not only about parameters, it's parameters combined with the water level, with the ground conditions, then you can even apply the lower value of parameter but still have a failure. And this is the scenario here. Here you have even better reduction of the costs in both solution, even for the mean values and the lower values, since the parameters are much better than you expected in this conservative conventional design. We could
Thank you.
we could do you agree? Or do you need some additional explanation?
No. Thank you.
Because if
And
you
one more question.
okay,
Is it good at the beginning to say that to be opportunistic about the material, to say that the material is gonna behave good? So to start with construction, and after that, you just see how the material behaves, and you apply additional methods of
well,
retaining the.
yeah, well, it depends, of course, on the problem you are dealing with, but the most important thing is that you need to have a prepared solution for the if problem occurs. That means, for example, you are doing some deep excavation near the existing structure, like here, and you need to do this excavation, and of course you don't want this building to settle, to have some cracks or something, this existing building here, due to this excavation. And for example, you need to, it's very important that you are ready to have defined additional measure if you observe, if observation confirms the problem. For example, you are measuring lateral displacements of this object, you are measuring lateral displacements of this retaining walls, some pile walls, and you are observing the settlements of this structure. And you, for example, now you want to start to have the piles like this without any additional anchors here. So you want to be optimistic, you don't want to spend money on this, but you need to be ready. So if you come here, if you're at this depth, and you and this some cracks occur here or some displacements are measured here that are over, for example, 2 centimeters, there are some introduction to some problem, then you need to be ready to apply this additional measure. So you need to have it defined, because you could spend a lot of time if this is not prepared. Then if you don't know what to do, then you maybe bring the material back here to support this. You'll spend time. So that could also increase the cost. If you ask me for the opinion, I never like this to work like this. I would rather go for something that is most probable, something that is most probable. And if you even if you go for the Eurocode 7, some new, this new standard for the design, you'll see that they are suggesting for the initial design to do the some characteristic value. The characteristic value is actually a mean value of the parameters. That's a mean value, a bit reduced mean value, maybe 10 or to 15% reduced to the mean value. So the design usually the concept of the design, the main design, is defined according to some mean values, and of course it is then followed by the monitoring and observation, and then there is a there is some space to reduce the cost, but also there is some safety margin for some large problem to occur, like here if we excavate this and then we have large displacement and we have something we don't want to have. So I would always suggest you to go with the some mean value of the parameters, and it's also in accordance with the design codes that are used, and that is characteristic values, the values of parameters they score characteristics. But for a very complex problems like this, like highways passing landslide, then I still think that mean values will not bring the cost so much in comparison to some observational method combined with the lowest, with the most optimistic parameters at the beginning, and then to because there are so many other problems that could can be like some relation between the investor, contractor, the construction period, and so on. I don't know how is it defined in your country and elsewhere in the Europe, but here in Bosnia and Herzegovina we have so-called the legal frameworks that contribute to promotion of this observational design, since we have the project, the design documentation defined on so many stages, like some, it's all marked with the documents G1, then it's go G21, G23, and then it's defined as G31, and then G41, also a G32, and then we also have a G5. This is something like um, conceptual design, and this is a main design, and this is the review of the main design, and uh, this is the this is the detailed design. So detailed design prepared by the contractor, and this is the revision of this detailed design. So here you have a contact between the investor, so the supervision engineer that is a that is defined by the investor, and the contractor that is who is preparing this mission G31s, or so-called detailed design, that is also supported by some observation of the geotechnical works. So here you have very important, so legal framework, really defined documents where the contractor and investor are connected, and you can apply this observational method for such a project. And the final document is this G5 document. That's actually some kind of forensic document that needs to define who is guilty for some problem if the problem occurs after the construction of the highway or some other structure. So if something like this happened, then there is a missing G5 to say why did this happen, and actually who will pay for this, who is responsible for this to happen. So I don't know in your country if it's possible to include all these observational method principles and to build it in some framework. But here from in the last 15 years, we have this additional regulation for the geotechnical works. They're set like this in so many of these books that sometimes are sometimes they're very appropriate for this very complex constructions. Once again,
Thank you.
observational methods is applicable for the design that are governed by the serviceability limit state. So where when we are discussing the displacements, and not in some problems where some failure can occur in a very short period. Okay,
Thank you.
any more questions, any more discussions? Some of your experience to share or something?
Can I ask something from the previous session?
Of course, anything.
You mentioned from the Eurocodes and the standards in Bosnia and Herzegovina, and you mentioned that boreholes are meant to be from 20 to 200 meters. So when constructing a highway, when designing a highway, if it's, for example, 50 kilometers long, does it mean that every 200 meters there has to be a borehole?
That's right. At least that's the minimum of the minimum for the main design. If you have 10 kilometers road, you need to perform a borehole at least on every 200 meter. What you mean? It's enough or it's not enough? Or it's too much? What do you think?
No, my question was yes. I mean, I just want to know if, for example, 50 kilometers, because that's a long distance. So if there's going to be in every 200 meters, that means that there are going to be a big number of
Why not? Why not?
boreholes
Actually,
to the alignment.
my experience is this number is actually not enough. For example, if I return to this presentation, let me show you some. This is here. This was the investigation work and monitoring. Let me just share this. If you see this picture, if you follow the rule, this is from here. Here is the tunnel, and these are 1 kilometer. These are 2 kilometers. Three. This is maybe 3 kilometers. This line from here to here. 3 kilometers. If you divide this, it means 15 boreholes. It is 5 boreholes in 1 kilometer minimum. So that means 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. That's every 200 meters. But if you see this, before the construction of this work, it was performed 1, 2, 3, 4, 5 boreholes only at this last maybe 300 meters. Or here you have a very deep excavation here that needs to go like this, and then let's go to the viaduct here. In this excavation that is going looks like this, it's maybe 100-meter long. 1, 2, 3, 4, 5 boreholes were drilled here to define the solution for this problem. So what I think is that this minimum at 200 meters for the line objects like highways is definitely not enough for the special condition, very special condition like here. The location, the highway location where 200 meters was appropriate, it could be the north part of the Bosnia where you have a river Sava and flat area all around it, where the conditions at 10 kilometers are practically all equal. And it's, I don't know, it's some clay material and some gravel, it's sand, clay, sand, like some cake with some layers of alluvial soil, sand, gravel, clay, sand, gravel, clay. Here you cannot miss a lot, but in this kind of conditions with deep excavation, with landslides, you always need to have this cross section. You always need to have this. And that's why I think that this what is defined as minimum in this design code, actually it is it is only a minimum. You should not follow that when doing a real investigation work program, and the particular values of the borehole's location should be actually defined with an investigation work program, investigation work plan that should be very deep, analyzed in details, because it can really influence a lot the construction cost, the changes of construction cost, the, I don't know, even the construction period. For example, this is where right now it's under construction. This part, these 3 kilometers are under construction, and the boreholes are performed exactly according to this in every 200 meters. Of course, somewhere it was a borehole, somewhere it was a trial pit excavation. Once again, borehole, trial pit, and the information gained from the data are so not enough. And now a lot of changes of the design solution are underway, and it will bring a lot of cost cost increment and a lot of construction time increase. So nobody is happy with what's happening here. But one of the main problem was the not enough not enough investigation work, and relatively poor investigation program plan that really follows the rule book. But that's really not enough. That's really not enough to follow the rule book for the conditions like this. Okay, any more questions? Not, we should open this next presentation. It's topic 4, and it's about retaining walls and drainages as landslide mitigation measures. Plus the discussion about foundations that need to be done in the landslide area. So this will be some kind of general story about retaining walls types, but then we'll include some landslide remediation measure and some practical examples of this viaduct founded on the landslide that we show at the just before this landslide that passes the landslide area, and the highway that passes landslide area. So what's the main idea of this section? Is just to introduce you different types of remediation measures that are mostly used. And you can see some of them here. When you have the highway passing landslide, then you can do this kind of a rock-like material that would be some kind of counterweight of the slope. If you have a slope like this, that is sliding like this, and then you want to do a highway here, then you may try, and the water level is very high up, then you may try to excavate this and change all this with some crushed rock material to try to reduce this water level, to try to increase the safety factor of this slope. In some other condition, you can use the construction like this. These are so-called grid structure that can be defined of vertical or vertical and horizontal beams connected here, and then additionally supported by geotechnical anchors. So when you have this like this, then you apply here this usually pre-stressed geotechnical anchors to support this potential sliding here. Also, I'll present you some well-known highway section passing the landslide area, and I'll discuss about some details and problems occurred there. One of the most simplest and well-known retaining wall types are this so-called cantilever retaining walls. This is one example of cantilever retaining walls that was failed during the construction, and you can see this part actually failed. This one did not fail, and it was temporarily supported from this side by this granular material. Later, some supporting with anchors and concrete blocks will be performed here, and this part of wall that failed will be changed by a similar but different solution of design. Another possible retaining walls type that can be used in the highway construction, not only in landslide areas, but anyway, when you need some change of the levels, it's so-called reinforced earth walls. So I'll show some details and main aspects of these two wall types. Also, I'll introduce this very special type of retaining walls that are not very much used worldwide, but these are really popular here at, at our place, and it's it's really cost effective, very economical technique to define a deep founded retaining walls that, and this solution is actually a change for a deep foundation with piles that is much more expensive. What is it about? Well, you build this concrete block in soil. This concrete block is excavated with this digging machine, and then it's filled with the concrete, only leaving the reinforcement up here as a connection for this wall footing. So this full footing is actually supported by these counterfort spades at every 6 or 5 meters. In the end, you have the wall like this, at this highway section. Actually, down below, you have a counterfort that is very deep founded, like here. So this wall could not be this relatively deep wall, relatively high wall. It's 4 meters, and it's a in a landslide area. We'll have this exact wall in details. We'll explain it in details when we come to the chapter of case studies. So there'll be time to discuss some details. Some other types of retaining walls, these are like very complex structures, cut and cover tunnel. One of the example that was constructed about a year ago. Uh, this Zenica by Spice. So this was a very deep creep slope. So you have even about 20 meters or 15 to 20 meters deep sliding that is very slow, like 1-2 centimeters per year, similar to this landslide I showed you before. And then you need a construction to pass the highway, for example, here. And what is it done? It's done that you build one pile row here, the other pile row here, the other one here, and then up above we have this structure, and all that structure is actually then filled with the excavation material. But it was not so easy to excavate this, since this is relatively poor material. If you excavate this, the failure could occur like this. That's why additional pile rows were constructed uphill. So 2 row piles were constructed here, and even up have one pile row that pass this landslide depth and go down into this better material. So we have some piles that support this temporary excavation, and then after you fill this, you can fill this with this to support this in total. So it's relatively complex even to reach this level to construct these 3 rows of piles, and then you construct this arch, and then you fill it with this excavation material. This is also an example of the stabilization of the excavation by vertical beams that are anchored. This is an example of this grid structure with anchors at every connection between vertical and horizontal beam. What you can locally see is also these subvertical horizontal drains. So when you look at the cross section, this is the beam system. Here are the anchors, and here you have subvertical drain. It's a 3 to 5% slope that collect the water, and water seep through this. So it's perforated here, collects the water, and then water seeps out, goes out from the depth of this slope. Here are some main aspects of designing, of shaping these cantilever retaining walls. For example, if you need a wall that is h in height, then means that it's this footing of this wall needs to be at least 0.4 to 0.7 of this height. So if the wall is 5 meter in height, then you need about 3 meters of footing. So this is 3 if this is in total 5. Regarding the depth of the wall, it's usually 10% of total heights. So it's 15 centimeters at the bottom for 5 meter walls. At the top, you can do a reduction of this height. It's usually never less than 30 centimeters at the top. The typical construction sequence of this wall, if this is the ground level original, then you need to do the excavation. After that, you apply the lean concrete, and then you install the reinforcement of the footing, and you also install these anchors for the wall, and then you concrete this part here. After that, you prepare the formwork for the wall, and then you insert the reinforcement, and then you apply the formwork, and then you do the concrete, the rest of the wall. After that, you're filling this wall usually with a good quality material like crushed rock or gravel. For the height, for the lower heights of the wall, you can use the backfilling of the granular materials at the bottom part of the wall and this part of the wall, and this can be backfilled by the material from the excavation, some coherent material, especially if you're not planning to have up here some pavement like or concrete or some road or something. If it's just a some grass or some soil, then you can, that's one reason more to apply here the material from the excavation. Since this material is a lot more expensive than the material from the excavation, this well graded, good quality rock material. If there is water, you can apply drainage here, or you can also put the weep holes here that are usually some pipes 10 centimeters in diameter, spaced on a 2 or 3 meters. The construction phases are shown here in some photographs. Here is the excavation. Then you have a reinforcement of the footing. Then you have a reinforcement of the wall. And then this is a drainage pipe. These are some details, construction details of connection between segments of the wall. If you build the wall in segments, and you usually do, since it's not it's not very good to excavate all the wall, since some local failure could occur from the uphill. So it's better to prepare this excavation in segments. Here are some additional details of this deep founded walls on concrete blocks. Here is how it looks in a cross section. This is a typical cross section that highway route passes here, and up above is some local road. And then, if you want to build a retaining wall that is founded here, then it would be really too high wall. It would be over 10-meter high. You would need to do excavations here like this. It would enter this expropriation area. It would definitely be be possible to prepare this solution. But if you prepare a relatively lower height wall supported by the counterforce, then you can combine. Here is how the counterforce looks like. Here is the excavation process of the counterforce. So the counterforce are locally built at spacing of 5 or 6 meters or something else, depending on the soil condition and the calculation results. And here you apply this footing. So this is first excavated here, and then the counterforce was constructed. Then the wall was constructed, and it was backfilled with this material. Only after that, this excavation was performed here. Of course, the restriction for application of this solution is the depth of this channel's counterforce. You cannot dig this deeper than about 6 meters. So 6 meters is something that you can reach with this machine. So this is very good if the foundation depth is such that the excavation doesn't have to be over 6 meters. If that is the option, then you can use this. It's much cheaper solution than to build some piles here or two pile rows or something else. So this is this wall. The typical thickness of the concrete blocks is the width of this excavation uh, machine. So it's around 1 meter, while the spacing of the contraforce, so one contrafor now is here, the other one is here. Its thickness is about 1 meters, and the spacing is about 5 to 6 meter usually. Of course, it needs to be calculated, checked by the detailed design. As I said earlier, we'll show the details in the case study section later. Reinforced earth walls, it's gaining popularity here at our place worldwide. It's very often used solution for the retaining walls, especially in United States. I don't know, in Turkey. It's very often used design solution worldwide, but there are no examples of constructed walls like this in Bosnia before last 4 or 5 years. So the first walls of this type were constructed in the last 5 years. Nowadays, there are plenty of the construction like this under construction, so it's really getting more and more popular even for a place. What is it about? Well, we have some facing elements that are very relatively thin facing elements connected by the different types of reinforcement. The reinforcement can be some kind of steel strip, it can be some polyethylene strips, it can be high density polyethylene or polyethylene geogrids. So these are called geogrids, these are called strips. It can also be a different kinds of geosynthetics. What we usually use here is or geogrids, these PET geogrids or PET strips. So or strips or geogrids that are on the polyethylene material. Once again, some typical concept that needs to be followed during the construction from designing of these walls is that the wall width should be about 70% of total height. So if the wall is 10-meter high, then this B should be around 7 meter. Additionally, the vertical spacing of the reinforcement should be around 0.5 meters. So these two aspects, if you have in mind, so that the B is about 0.7 h and that the vertical spacing between the reinforcement is about 0.5 meters, you already solved many problems that could occur with this kind of walls. Additionally, you just need to select the appropriate ultimate strength of this reinforcement to prevent breakage during the tension in these reinforcing elements. One interesting diagram compared the costs of the wall in dollars per square meter of the face of the wall, depending on the wall height. So when you have a relatively deep walls over 6 meters, you will see that the geosynthetic reinforced earth wall range about $300 per square meter, while the cantilever walls are about $500 per square meter. So it's not double, but probably 1.5 times cheaper is to select this reinforced earth wall, and that is definitely why these kind of construction are used more and more, not only worldwide but also in the local practice. Here is the example of reinforcement, backfilling, and compaction of the material. So the wall is constructed from the bottom up. So you apply facing elements and reinforcement, and then backfill it. Once again, second layer, and then backfilling. One additional layer, and backfill it, and so on from bottom to the top. What's the bearing mechanism of this kind of walls? It can be illustrated by the mechanism of this pyramid shaped by these tennis balls. If you shape them to form this pyramid and you press it by hand, you'll see that it will spread all around. But if you put around this triangle, you'll see that this Q value is much, much bigger than higher than Q1 values. You probably maybe won't even be able to separate these balls one to each other. That's exactly what these reinforcement do. It brings brings this non-cohesive materials and preventing it from failure, from separating these particles from one to each other. Since there is so many of these walls, one interesting paper was reported in the literature where total of 171 walls were were observed within the failure or large displacements of 171 walls occurred. Actually 44 cases with very large displacement and 127 cases of collapsed totally failed walls like it's shown here. So this paper discuss about why this happened, what are the main reasons and some statistical aspects of these failures. And these are really, I'll underline some interesting conclusions. The first one is that practically all the failures occurred in the period of less than 4 years after construction. So if you have a wall stable for 4 years, you can be quite sure that it won't fail after 5, 6. Of course, there is some percentage of this, but most of walls failed in this period. Practically all the walls failed due to improper design or construction. And most of the walls caused by the water that came from outside of the insides of some surface drainage or outer water. So the main problem is actually water. If you see one thing is also this one more than half of the walls. This one is important. 60% of the walls that failed actually used a clay backfill in the rainfall soil zone. So here in this area, clay material was used. That's something that is not practiced and that is not suggested. It's always suggested to use granular material as a backfill. And what we usually have here at local practice is to use a crushed rock. So you do the excavation at one part. If this is original ground, you do the excavation here and then you install it here. And that's usually some crushed rock material, or it could also be a gravel or sand, but that's not material that we have so much. We usually have this crushed limestone or some other rock type. This is the usual failure mechanism that is observed here, and it's the detail that is not good to bring the water from the surface in this reinforced area. So if you have some pipe here in this wall area, then this some internal water erosion can cause the failure like this. That is progressively. So this is bad detail. This is good detail. This is also a recommended good detail to put all the surface water around the wall, not inside the wall. Because if you have this, then you have the initiation of failure here that spread here, and at the end you have a picture like this or like this. Okay, we are now about to end this second part. Let's continue in 5 minutes with this remaining part of the presentation, because now we'll be interrupted by this 40 minutes, I think.